Hi, I'm Siva and I'm excited to present LidarSim. A critical component to making self-driving vehicles a reality is verifying they are safe. But how do we evaluate SDVs? The self-driving industry uses a combination of three different approaches. First, there is structured testing, which tests the SDV under a set of reproducible scenarios. While effective, it's difficult to test extreme situations, such as high-speed avoidance maneuvers. Additionally, large-scale testing is impractical. We can also evaluate the SDV on pre-recorded real-world data. However, the sentry data and other actors' behaviors are not updated according to the SDV's actions. It's also still difficult to test safety-critical cases at scale. The third method is to use simulation. While simulation systems have a domain gap with the real world, they are reactive and can test any safety-critical scenario easily. Unfortunately, to test the full stack, we require sensor simulation, but currently it is not scalable due to the prohibitive cost of handcrafting 3D virtual worlds. In this paper, we focus on making full-stack simulation systems more realistic and scalable. Importantly, by unlocking scalable sensor simulation, we not only have comprehensive testing, but also annotation-free data augmentation for training perception algorithms. We now review the SDV system and how we inject simulation for evaluation. An SDV ingests sensor data, perceives and predicts agents' behaviors, and then plans a safe path. Traditional simulators only simulate bounding boxes and trajectories, enabling only motion planner evaluation. End-to-end closed-loop testing requires simulating the sensors of the self-driving car. Thus, given a traffic scene layout, we want to simulate realistic sensor data. We focus on simulating the LiDAR sensor, prevalent in self-driving. Prior work in sensor simulation, such as Carla and AirSim, simulate LiDAR by designing 3D assets by hand, building a virtual city, and then physics rendering the LiDAR. Unfortunately, it's expensive to create assets, it's not scalable to have virtual worlds for the numerous cities we want to test in, and the simulated LiDAR is unrealistic. To overcome these challenges and generate realistic LiDAR at scale, we leverage millions of real-world miles collected by our fleet of self-driving cars to help build virtual worlds for autonomous vehicle testing. Here, we show the process of how we generate realistic backgrounds. We record real LiDAR data by driving in an area and removing moving objects. We aggregate and align this LiDAR, combine across multiple trajectories, and then create a mesh circle representation. A similar process is done to generate thousands of dynamic objects. Leveraging real data allows us to inject the diversity of objects seen in the real world into LidarSim. Once we generate our assets, we can place them in a scene configuration, just like in a video game. We now have scalable and diverse scenes. We then perform realistic sensor simulation with physics and machine learning. LiDAR generates point clouds by shooting light into the scene and measuring the travel time to determine an object's distance. To mimic this process, we raycast our scene and generate a simulated point cloud. However, raycasting generates more returns than real LiDAR, since the returned light does not always meet the detection threshold. We call this phenomenon ray drop. Ray drop is complicated to simulate by physics alone because we don't know the physical parameters of our real world. Fortunately, using a ray drop network, we leverage real-world data and machine learning to bridge this into real gap. We convert each LiDAR sweep into a spherical image representation, encoding features related to ray drop, such as range values, incident angles, semantics, and path intensity values. We then feed these features into the network and predict how likely a ray will be dropped. The labels come from real LiDAR ray drop patterns. We sample the ray drop probability to generate the final point cloud. We now show results. This side-by-side comparison shows LidarSim generates realistic point clouds with small domain gap for downstream perception tasks and autonomy testing. This perception model is trained on real data only. We now compare LidarSim against Carla, a state-of-the-art sensor simulator. A model trained on Carla data and tested on real data has a large sim-to-real domain gap. But a model trained with LidarSim has just a 1% domain gap, significantly outperforming Carla. The small domain gap means LidarSim is effective for data augmentation. By combining LidarSim data with real LiDAR, we get a significant performance boost for vehicle detection, with both small amounts of real data and large amounts of real data. LidarSim also allows us to evaluate a perception and motion planning system when delivering safety-critical scenarios in a closed-loop setting. The system, trained only on real LiDAR data, is able to process LidarSim data and safely brake to avoid collision. With no additional training or domain adaptation, we can directly use LidarSim to test an autonomy system end-to-end on millions of different scenario variations, achieving results that match closely with the real world and allowing us to gain new insights into the self-driving system. Thank you.